Hello students, we have done the discussion of previous three parts where we have taken the discussion about organic, inorganic and physical. Now the last part we are going to take the discussion about the general organic, general chemistry where we have discussion about questions related with chemical bonding, calculations, we call mole concept, redox iterations, and also a few questions on structure of atom, which is related with the all other branches. So this is that same exam. We have IOQC 2022, 20th March exam was held. We are going to take the discussion about the general chemistry questions. We'll be starting with our section 1 first, which is single option correct. The very first question over here was, we have got the 0.805 gram of the potassium salt of some dicarboxylic acid was given to us. The molar mass was, the formula was not revealed because we had to calculate the molar mass. So this is dibasic, which means 2H plus acidic hydrogen will be there. 2H plus N can be given out, and that has been replaced basically by potassium. So to solve this question, what we have to do, we were given this much amount of the salt was taken, and then when this was reduced, this much gram of the potassium was remaining. Rest everything was converted to some other compounds. So this is whatever a strategy should be. The correct answer to this question was 118, and this will be the strategy what we should be following. The strategy that first of all we are having this much gram potassium coming from this much amount of the salt what we started with. Then we can compare if this much gram of the compound is being converted into this kind of dicarboxylate anion, because their molar masses can be related. Molar masses will be relating from the fact that 2 potassium means 2 times 39 gram of the potassium will be combining with how much gram of the salt. That will be the molar mass. That molar mass will be relating with this molar mass of dicarboxylate anion, and then we can put 2 hydrogen atoms to get the molar mass of this dibasic organic acid. So we'll see this calculation, how we should be progressing. This is the thing. So starting from the equivalent concept, because 2 potassiums are present over here, and the information given to us was 0.323 grams of potassium was reacting with 8.05 grams of the like this much gram of the potassium was coming from this much gram of the salt. Okay, then we have if you have got 2 potassiums, basically as per this, like if you take 1 mole of the compound, then there will be 2 moles of the potassium atoms available. So 2 moles of potassium atoms are going to be 2 times 39 grams. That gives you 194 gram of the salt, which is basically molar mass of this salt. Now what we are doing, converting that molar mass of salt into the molar mass of this dicarboxylate ion and then acid. So from here to here, what we have done minus 2 of the potassium and we have done plus 2 of the hydrogen. So what we have done from molar mass of the that salt, we are going to do minus of the 2 potassium and plus 2 for the acid. Doing so, we are getting 118. This is going to be the molar mass of this dibasic acid what we started in the beginning. Okay. Next question in this section is from the structure of atom, that is hydrogen spectrum. Pretty straightforward question. We know the that hydrogen spectrum, that Rydberg equation, and we can solve it. The answer to this question was n equals 4 to n equals 2. And because we have been given the things about helium ion, we have to find that the same transition which can be happening. This is having the same wavelength as n equals 2 to n equals 1 transition in hydrogen atom. So when we have got similar energy transitions taking place in hydrogen versus helium, what we have to do, we have had that Rydberg equation. We understand this helium plus is also one electron system, so that Bohr's theory can be applied. Hydrogen spectrum, that Rydberg equation what we have used, Z effective because He plus is having greater than hydrogen atom. So basically the electronic energy levels in the hydrogen and He plus are going to be different. So from n equals 2 to n equals 1, whatever energy is associated with this hydrogen atom over here, the energy levels being different in He plus, their different energy levels we should be choosing for the same delta E values. Or that electronic transitions will be basically going from some different values of n1 equals n2 when this excitation is going to take place. So what we are going to do is we are writing this expression for the Rydberg equation, where 1 by lambda was equal to RH, that's the Rydberg constant, multiplied by z square, 1 by n1 square minus 1 by n2 square. Now we are writing this expression for both the atoms, for the hydrogen as well as for the helium. Okay, so in the hydrogen we were given that Z is 1 and we were given the values of n1 and n2. So what we are going to evaluate is this term 1 by n1 square minus 1 by n2 square for helium must be equal to the same value onto the left. Here the value of Z is going to be 2, so that 2 square term is appearing into the expression for this Rydberg equation for helium atom. This is basically He plus rather than He. So now putting those values, we are going to evaluate, like here hydrogens N1 and N2 were given, this N1 and N2 we can be calculating. So the value of the N1 and N2, like 1 by N1 square minus 1 by N2 square will be turning out to be 3 by 16. Now, this 3 by 16 can be satisfied by 1 by n1 square and 1 by n2 square, where the possible values we can start. n1 can have possible values 1, 2, 3, 4, etc. And n2 can be having its value starting from 2, 3, 4, etc. So we can see this can be this condition where 3 by 16 is that it can be satisfied only when n1 we are keeping as 2 and n2 we are keeping as 4. So this thing is turning out to be 1 divided by 4 minus 1 divided by 16, which is same as 3 by 16, right? That was the relatively straightforward question. We need to just put the things value in the expression and we'll get the answer. Moving on to the next question. This question is based on the structure of atom. Once again, we have got the quantum mechanical model, and this is pretty interesting question. They asked the concepts related about the subshells we have an idea of or not. We also should have the sound idea about the quantum numbers and those nodes. If we have these things, we can get this question correctly. And see what they wanted us to find. Basically, they're asking us, we have to find the maximum number of electrons which have got the value of spin quantum number as plus half. When they're saying half, we mean to say it is plus half, because otherwise they'll say it's minus half, which can be accommodated in the subshells. So when we are saying subshells, say we are talking about some p subshell, so there can be those 3 different orbitals. When we are saying subshells, that should be px, py, and pz. Basically, that is what the basic idea of this question was. And now when we are saying this, all this thing is happening when the orbitals are having total of 3 nodes. Like every subshell or whatever orbital we are choosing, the every orbital of the given subshell must be having total 3 nodes present. And when is that going to happen? We can see when we are talking about 3 nodes, there can be a possibility of radial nodes as well as angular nodes. We'll work on all those possibilities and we can see that answer will be coming as 16. So this is our strategy, how we'll be going at. We have 3 possibilities for 3 nodes, basically 4 possibilities. That one is there should be 0 radial, 3 angular nodes, like all are the radial angular nodes only. And then we have got the 1 radial, 2 angular, 2 radial, 1 angular, and the last possibility, the 4th possibility, 3 radial nodes only, and 0 angular node basically. So this strategy will be giving us how we can be finding how many orbitals are associated. So the orbitals which are basically, first of all, we can see how these orbitals are going to be. So this is one of the 4f orbital, and here basically we would be having 3 different nodes, and all these nodes are going to be angular nodes only. Here we have angular nodes only. The 3 nodes what would be present, one is going to be present along this line. This is very lightly colored. I am not sure whether you people can see it correctly or not. Basically, I'll be trying it once again. That node, that particular plane is going to be the radial node number 1. That is basically, we can say, is the XY plane that we have kept over here. So this is going to be your XY plane as first node. That is the nodal plane, we should say. This is nodal plane, and there will be 2 nodal cones, what we have seen in dz2 kind of orbitals, which would be presented, oriented basically like this. That is one of the nodal cone. That is second angular node we say, that is called as nodal cone, and the similar nodal cone is going to be present in the other direction as well. Probably you can see that little grayish outline over there. That is going to be basically the another nodal cone, that is nodal cone number 3. This one. So this is how we are basically going to see that total nodes are going to be there. Here all the 3 are going to be the angular nodes only, whether it is nodal cone or this nodal surface. This total value was going to be 3. This was some of the 4f orbital. And now we are talking about this is 4d orbital. In this 4d orbital, we are going to have one radial node. First of all, I'll show you where that radial node is basically present. So you see this inner region of this 4d orbital, and so here basically along this particular boundary we will be having some region where there will be no electron density present. This thing is what we are calling as the radial node. That is first node we are talking about. This is 4d orbital, and this earlier was our 4f orbital. Right, this is one of the radial node, and there are going to be 2 nodal planes in this orbital, and we have basically shown here this orbital which is going to be having one nodal plane which is going to be present along this YZ plane. We can draw the outline of that YZ plane. I'll choose white color. So that is basically the plane we can think of. That is one of the nodal plane, that is YZ. Okay, here we need to write here. This is going to be YZ plane is one of the nodal plane, and another nodal plane we can see would be lying along XY plane, which is going to be present somewhere like that. It was actually shown in those very light brown colors. It is, and the black background, it is not very clearly seen. If you could possibly see in the video, it is very much good thing. If you cannot see, we can think about this as going to be XY plane. This is going to be another angular node. So this is going to be node number 2. This is going to be node number 3. 3 nodes are present once again in this orbital as well. The next example we have got, this is your 4p orbital. In this 4p orbital, what we are having total 2 of the radial nodes. So here we had got one radial, like this was the 4d was the case. 4f was the case where we have got 3 angular nodes. 4d was the case where we have 1 radial and 2 angular. In this 4p, now we will live in situation there is only one angular node, and there will be 2 radial nodes. So here I write we have in this case 2 radial and 1 angular. Angular node is basically a nodal plane. So that nodal plane is here is going to be along that this YZ plane, which we can draw maybe something like that. That is very lightly visible, that brown outline. That is going to be your YZ plane. That is going to be the one of the angular node. And the 2 radial nodes over here we have to see. You can see those phase signs getting inverted. First thing, this first of this shot is happening over here. That white and yellow regions, what we are seeing over here, they are being interchanged. So along this particular line, we are going to have what we can be calling as the first radial node, and along this another line, I'm drawing it in green color. Along this line again, you can see the phase change taking place, and basically that region along which we are drawing, there will be no electron density present. That's going to be the second radial node. right? That was 4p orbital. The last orbital, this kind of thing is our this is what we are seeing is the 4s orbital. Here there are going to be 3 radial nodes only. No angular nodes are possible in s orbital. That is what we have learned. So we can see the first radial node is present here. Maybe I need to choose another color. This is this is the first radial node. Sorry, that was the second. We can say this is the first radial node. That was where where the signs are changing. That is the second radial node, and here we can see is the third radial node. So that's how we can see there are different radial nodes present, and this is going to be how we can think about these different nodes and these different orbitals. Okay. So 3 possibilities what we have seen. We can count the number of electrons now. The first thing, when we had 0 radial nodes and 3 angular nodes, that was the possibility of some of the 4f orbital. And in this 4f orbital, we have got 4f subshell, we should say. We have got 7 orbitals, and in the 7 orbitals, the electrons which are having the value of ms as plus f are going to be 7. Just like that, we can think about 4d orbital, and this 4d orbital, we will be having total 5 such orbitals. There will be 5 electrons present. Coming to the 4p, we will be having total 3 of the electrons present. 3 such electrons will be present over here, and in 4s, that is the last orbital, 1 such electrons are present. Putting these things together, we have got the 16 such electrons possible with the given conditions. So that was the correct answer, which was the 16. Interesting question, a good way of testing the concepts, whether we have learned it correctly or not. Going to next question, here we have got some ionic species M3+, and this is supposed to be isoelectronic with CuCl2. Again, they have actually put the question which you can correlate very easily, and most of the students might not have seen these kind of questions earlier. They just need to apply their concepts. That was the idea. And they're saying this M3+ ion what we are having, this had Z plus 2 neutrons. So we have to find the molar mass. You need to follow what they are saying. Now, the correct answer was 134, and how we are going to solve this thing. First of all, we'll find the electrons which are present in CuCl2, and let us say this number of electrons. So we basically be counting the number of electrons present in copper 2 plus number of electrons present in 2 of the Cl- ions. And then if these are x electrons, that means the M3+ ion will be also having the x electron. Now, if M3+ ion has got x electrons, we can now find how many electrons would have been present in M. Basically, 3 extra electrons would be present because loss of 3 electrons will be giving us M3+. So basically, we know the number of electrons in M. That will be giving us the value of Z for the M. And then we have been given Z plus 2 electrons are present. So we'll put the number of electrons and number of protons. That's going to be the basically mass number. And because nothing other information being given, we'll be saying that mass number will be related with the molar mass numerically to be the same. So that is the thing how we have started solving it. That copper is having 27 electrons present, chloride is having 18 times to 36 electrons. So total electrons in this CuCl2 are going to be 63, and we are now going to say the same number of electrons are going to be present in M3+. So M has going to have 3 extra electrons, that is 66 electrons are present. That means this M, the whatever that element was given, this is having 66 electrons present, and as it was given, there are Z plus 2 neutrons, so neutrons are going to be 68. Put these things together, 134 is going to be the molar mass, or mass number. Basically, we can relate that as the molar mass. Pretty straightforward. Just need to put whatever they are saying, follow the things they are giving, and we can get the answer. Relatively easier. Moving on, here we have got some question related about the data sufficiency we can possibly think, and not data sufficiency, we are being given some experimental error. It can be happening later. So how we can correct that happens actually number of times in the labs. We are doing some experiment, we are thinking of something else, we are getting our calculations done, and then later we realize that we might have done some mistake. So how we fix that? This question is about all that. We have been given some 100 ml of 10 ppm solution. K plus was being prepared from potassium chloride, but unfortunately, like every process was adopted using that. But unfortunately, something went wrong. It was realized that the compound which we started with as KNO3, that student who was performing that experiment, he has taken the KNO3 rather than using KCl. So now what he supposed that it was 10 ppm solution, the actual solution what we'll be getting, it will not be having the same ppm concentration for the potassium ions. What would be its K plus concentration that we were tested? One of the options also they gave, it is going to be 10 ppm itself. Do you realize this 10 ppm would have been the answer if we were asked the 10 ppm solution of KNO3 versus KCl, because this is not that this is K plus, the ppm is going to change. So how we'll be following 7.37 is the answer. How we'll be following is, first of all, we will be finding that for this 10 ppm solution, how much KCl would have been dissolved to get the solution. We can assume that X grams of this KCl would be needed. Now, taking from X gram KNO3, how much K plus would be generated, that also we can calculate, and basis on that we can find the final concentration. So here is the actual calculation. So the 10 ppm solution actually means that if you have taken 10 to the power 6 gram of the solution, you would have got 10 grams of the potassium ions, right? Now, although that solution which was prepared as 100 ml, we will be doing our calculation from this thing. This will not modify our result. In both the cases, we'll be assuming this is the same thing, because the concentration terms are going to be intensive properties. They're not going to be dependent. They are going to be intensive property. They are not going to dependent on the how much amount you start with. Whether you prepare 10 to the power 6 gram solution, 1 ml solution, 100 ml solution, the ratios are going to remain exactly the same. So we'll be starting with the same value. We could have corrected it basically for the 100 ml. We would have got one extra term. We are just skipping that. So now, when we have this relationship of the K plus ions and KCl, that 39 gram potassium is present in 74.5 grams of the potassium chloride. That's their molar masses ratio. So now, if we have got a 10 ppm solution, then how much KCl that student might have weighed? So basically, we are saying that if 10 to the power 6 gram solution would have been prepared, then we would have weighed 91.1 gram KCl solution. But we understand for 1000 ml, basically the student, rather than weighing 19.1 gram, he might have weighed 19.1 milligram. That can be adjusted accordingly. That's not a problem. So now what we are going to do, keeping these values in gram, we are going to do the calculations. So now we have to, as what we have taken as 19.1 milligram, basically gram, we can come back to this. What we might have taken as 19.1 gram as KCl, it was not KCl, it was KNO3. So now we will be correlating that 19.1 gram KNO3, basically if it is there, then how much potassium we will be getting. So now we will be correlating the molar masses of KNO3 versus potassium, and that is that 101 gram of potassium nitrate is going to give you 39 grams of potassium. That's the molar mass ratio. Now what we weighed, it was not KCl, like this much gram, assuming that 10 to the power 6 gram solution was prepared. What we weighed was not 19.1 gram KCl, it was 19.1 gram KNO3. So what will be the actual value of the potassium ions present? 19.1 gram KNO3 if you take, you'll get 7.37 gram potassium ions. And as we have said, assuming this is present in 10 to the power 6 grams of solution, that is going to be the value of the ppm concentration as per definition. So 7.37 will be the answer for this particular question. Okay. Interesting. If you have been in lab, you might have seen this kind of situations maybe sometimes. Or if you are following everything correctly, then nothing goes wrong, then you are okay with it. So this is basically the way how we can be solving this question. Moving on. We have got this another question based on significant figures. That is what you people mostly learn in the physics, the very first chapter. Never mind. Here we have the answer as 40.000. They had asked basically which was the value in which all these zeros are significant. So for that, basically, we need to follow those rules which are there for the significant figures. And if you follow those rules, we can find the answer. Maybe we can have a recap on what were the rules for the significant figures. First rule was, if you have got any non-zero value, this is always going to be significant. Then it comes to 0. So when we have got any zeros between two significant figures, they are always significant. But when there's are trailing zeros or leading zeros, then there can be different rules. So what we are saying here, this is the important point for our given question, that any final zeros or trailing zeros which are there in the decimal portions, they are only significant. If you don't have the decimal points, then the trailing zeros might not be. So here we have an example. If you have got 0.500, 0.63200, these zeros are significant. But if you have leading zeros like here or like here, these zeros are non-significant. So coming to our question, what we have got, the significant zeros and non-significant zeros, we could have seen the first option, these zeros were non-significant. The second option, the leading zeros were non-significant and the trailing zeros were significant. And the option number C, all these zeros were significant. That was our correct answer basically. And in the option number D, the leading and trailing zeros, that is how we can think about the significant figures and basically significant zeros this question was mainly based on. That was the answer number C. Okay, so next question we'll be taking is the from section number A2, where one or more than one options might be correct. The very first question in the section is, we have got this question about the data sufficiency. We have taken the potassium chloride and sodium chloride, and we have taken their equal masses, and we have dissolved them in the equal volumes of water. And these are done in two separate closed containers. In the diagram, although I have taken the open beakers, we can correct that, shouldn't be a problem. Okay, so here the correct answer was given as D, but there is a little bit doubt in that. We can talk about that. So what information we have been given, there are these two containers, and we have got NaCl and KCl in these two containers. In first one we have got W gram, and as per question we are assuming W gram. Second also we are taking W gram. In first one we have taken VML of water, and second one also we are taking VML of water. Now based on that, what we can do, can we do approximation? Can we do the data sufficiency validation? This is what we are going to see. Okay, so the first thing that was happening is the molar mass is given. So what we know, sorry, the molar mass we can calculate. The mass was given, molar number of moles we can know from the molar masses. That's very much obvious. But what we don't know and what things are required for these different values, like for molarity, what we need the volume of the solution. But how we can know the volume of the solution? This is the volume of the solvent taken. When we are putting this in NaCl, we need to keep in mind that when these two things are mixed, they can be forming ideal or non-ideal solution. There can be volume contraction or volume expansion in different cases. So unless and until we have got very much clear idea about the density of the solution or volume of the solution, we don't have very exact information. So probably molarity cannot be calculated exactly. The exact value we cannot possibly calculate. But in the question, in fact, they had asked which can be compared. We'll be stressing that point in a moment. Okay, for the molality, again, the mass of the water is needed. We were not told anything about the temperature. So V milliliter of the water can be having different values. Although their a number of moles, their volumes are same, their number of moles are going to be different. So with the different number of moles, the exact values of the molality also cannot be calculated, although they can be compared, that which one will be less and which one will be more, right? So here also there will be a problem in the calculation of exact value of molarity. There will be a problem in the calculation of the exact value of molarity as well. The third option was mixing the two solutions. If you are having chloride ions present in NaCl and the KCl, so whatever chloride ion concentration we are having here, and what is chloride ion concentration we are having, they had given us in this option that the chloride ion concentration. We'll read out this as molarity basically. So the molarity of the solution, we can think about the concentration terms as well. They said if here the concentration, it says C1, here is the concentration at C2, then final solution will be having the concentration. This concentration is going to be C1 plus C2. That's never going to be true, because we have to do the total number of moles divided by total volume of the solution. So that also this is definitely not going to be the correct option. The last option, they told that if you are having the information what is given, this information can be used to compare their vapor pressures. Now, for the vapor pressure, we need to use that Raoult's law, which used to be delta P, basically, which is P naught minus Ps. So this vapor pressure for these solutions need to be related as P naught minus Ps divided by P naught. This is going to be I times number of moles of solute divided by I times number of moles of solute plus number of moles of solvent. In this question, we have not been given the Vanta factor I. If it was because you are not told how much W and how much V was taken. If this was a dilute solution, the I for these, they can be nearly 100% dissociated and I value can be nearly 2. If we are keeping it for diluted, then the extent of dissociation for these two solutions can be pretty much different. And if these two values are different, then this approximation what we are going to make may not be correct. So the comparison of the vapor pressure, we can possibly compare which one can be less, which can be having higher on the basis of the number of moles present. So the actual answer to this question was given as the option number D. But if we are doing the approximation in this option number D, that vapor pressure can be compared. With that reasoning, what I believe that molarity and molarity can also be compared, like which one will be less and which one could be more. The numerical values we may not calculate, but the comparison, which one will be less and which one will be more, we can definitely do that comparison, right? So the official answer key is going to be D, but that if D is correct, because here we are using the term what is the mole fraction of the solute and solvent. Again, the number of moles here for the water we don't know, and because we converted into W, will be having some density required. Once again, that value we are not. So here also we are basically using good enough approximations. We are putting those approximations here as well. We can do the comparison. Coming to the next question, question number 8. Actually, question 27 from the original paper. This question was based on the resonating structures and their relative stabilities of the those resonating structures into the resonance hybrid. So we have been given the values. The values are the actual values, what we find, and the values as per calculation for the sulfur carbon single bond, sulfur carbon double bond, and this is for carbon nitrogen single, double, and triple bond. This is given because in these three different resonating structures, we have got different bond orders for the sulfur carbon and carbon nitrogen. So whatever strategy to solve this question would be, we will assume first of all that these two structures, the first two structures are having equal contribution for the carbon nitrogen bond, or carbon sulfur, or double bond, or carbon sulfur single bond. So idea would be, if we think that these structures have got equal contribution in the resonance hybrid, then the actual value lies, if it lies closer to the single bond. Let us say we have got A and B, some atoms, and they are forming, in one structure they are forming single bond, and the structure they are forming double bond. And in the resonance hybrid, we find the bond length is closer to the AB single bond. That means the structure in which AB have got the single bond present, that will be having greater contribution to the resonance hybrid. As simple as that. So that information we are going to put over here, and we are asked which of the option is incorrect. So we will be choosing the incorrect options. The incorrect option is going to be option number B, which says formal charge on sulfur in the resonating structure number 3 is 0. It is not 0, it is something else. We'll be calculating in a moment. The actual answer key although said that option D is also correct. We'll see. So comparison will be done with respect to the actual bond values, which will be for the resonance hybrid, versus the values which are going to be the kind of exactly in between basis, on that we can compare. So the answer given in this key was B and D. This D we have doubt. D should not be the correct answer to this, because the option was asked which of the following is incorrect. Let's see. So what we are going to do is, first of all, we are finding the actual values. This was given in the data, And when we are finding the average of sulfur carbon bonds, this is for the single bond, this is for the double bond. Average is coming as 168. This value is closer to the double bond. This means the resonating structure in which sulfur carbon have double bond will be having greater contribution. First thing. Second thing, when we have got carbon nitrogen bond values given, we are comparing for the double bond and single bond. Over here, the average is coming as 137, and this value is basically much less in comparison to, like the value which we have for carbon nitrogen bond is 117. Here the average is coming as 1. Basically, this is not in the range only. This is 147, 128. So that's not possible that carbon nitrogen can be having any single bond character in the resonance hybrid. So what we can say, the structure in which carbon nitrogen single bond is present, that is going to be the least contributing. Okay. Now, coming to the carbon nitrogen double and triple bond, if we are going to compare, this is giving us an idea that this value is exactly midway, like the difference of 6 from here, difference of 6 from here as well. So this is going to be exactly midway the carbon nitrogen double and triple bond. So here we can say that that resonating structure which is having carbon nitrogen double bond and carbon nitrogen triple bond, they are equally contributing. So if you go back to the structure and check, then we will find the structure number 1 and 2. They were basically having the equal contribution. But the structure number 3, where carbon nitrogen single bond was present, that's going to be the least contributing. Now, out of structure number 1 and 2, if we need to check, we can see that that resonating structure. Actually, I wanted to show you that is here in this last part. We can come back to these formal charges point. So in this structure number 1, we have got sulfur nitrogen, sulfur carbon double bond, and carbon nitrogen double bond. And carbon nitrogen double bond, carbon nitrogen triple bond, these two structures are equally contributing, and these are relatively that structure which is carbon nitrogen, this is going to be the least contributing. Now, out of these two, first and second, which one we choose? That's the question. For that, this first point comes handy, that the resonating structure with sulfur carbon double bond will be more contributing. So this is the structure where you are having the double bond. This is going to be having more contribution. That's how we are putting these things together to finalize. This answer is going to be like the exact order for the resonating, like the stability of the contribution to the resonating structure is going to be the stability. Structure number 1, most stable, most contributing. Structure number 3, least contributing. So option number 3, option number C was the correct option. Option number 1, the canonical form resonating structures 1 and 3 are more important than from the structure number 3 that we have seen from the option number 2 from here. Now, coming to the option number B, formal charge on sulfur in the structure number 3 is 0. Here we have done the calculations of the formal charges on the basis of the number of bonds being formed and the number of lone pairs put together. We have got some formula we can put in that, or we can see how many charges it is going to have. So when we are saying the first structure, only nitrogen is having one extra electron, that's going to have the negative charge. And in the second structure, sulfur is going to have an extra electron. Over here, sulfur is having 6 electrons, and there is one bond formation also taking place, that's going to have negative charge. Rest all things were normal. So in the second structure, basically nitrogen is having all 5 electrons, 3 bonds are being shared, so there is no extra electron, so the negative charge over here was not there. The nitrogen should be having the 0. The formal charge on the nitrogen, this option said, in the structure number 2 is 0. This is the correct statement, and we were asked about the incorrect thing. So this should not be the answer in my opinion. Let's see if they change it later. We have a time to challenge the questions and possibly get the keys correct. They possibly will change. Okay, so that was this is the last question in this paper on the general organic chemistry. We have been given some compound, and in this compound we are seeing here that phosphorus is forming bonds with these different compounds all around. One, it is bonding with the bromine, another one it is bonding with the oxygen with double bond, oxygen single bond, oxygen single bond. Now what we have been given, the percentage S character what this phosphorus atom is using. In the PO bond, it is using 40%. In PBr bond, it's using less than 20%. In PO bond, it is using 20%. So the idea is the different orbitals which are being used for bond formation, they are not having the same hybridization. They are having different schemes of hybridization. This is something what we call as isovalent hybridization at the central atom. We are being asked that difference in this percentage as character of the phosphorus bonds could be due to. We are being asked for the possible reasoning why that would happen. Basically, they are saying that this bond, the phosphorus oxygen bond is going to have, phosphorus bromine bond is going to have the least percentage of S character. Possibly, they are saying this bond is going to be the longest bond out of with respect to the phosphorus using its hybridization. And this bond is going to be probably the shortest bond. We also can think from one aspect that shorter bonds are going to be relatively stronger and longer bonds are going to be relatively weaker. One of the idea of this bond strengths can also be there, and another idea can be coming from the bond orders. Like if you are having higher bond order, you can expect the central atom can be using relatively more percentage of S character. Like you can refer back to the alkenes, alkynes, and alkanes. That is one thing what we could have seen, or any such compound for that sake. So here the correct answer is going to be the first option. The largest size of bromine atom can be trying to move as away as possible, because otherwise there will be quite repulsion. So if you are going to form a longer bond, you need to increase percentage of P character and you need to decrease percentage of S character. That can be one of the correct reasoning. Maybe we'll see in a moment. And there can be something else also. Basically we can see. Then second thing is that increased overlap of the second option was the large difference of electronegativity between phosphorus and oxygen. Actually, this, if you apply the Bent's rule, can be going wrong, because what we have learned, oxygen is more electronegative in comparison to bromine. So that if you go by that, then oxygen should be using more percentage of P character to form a bond. But on the other hand, if you see the values, we are trying to see that oxygen is actually forming the terminal oxygen. This is we are calling in some of the cases a terminal oxygen. This is forming this here. This is terminal P bond. This is forming relatively stronger bond. For a stronger bond, you should be having those atoms approaching, their nuclei should be approaching closer, so that electrons can be more tightly held. That would need the orbital, the hybrid orbital, to be relatively shorter. That is where phosphorus oxygen, where the bond order has been increased, is going to use relatively greater percentage of S character. That is one of the very like simple reasoning what we have seen in the chemical bonding when we were doing the different schemes of hybridization of central atom in the same given molecule. Then in option number C, they are saying, so that increased overlap of the sigma orbitals of the terminal PO bond can be the reason. That is what we have said just now, that if you have to form a stronger bond, it need to be a little bit shorter. And if it is shorter, which hybrid orbital is there which can be having shorter bond? The one having more percentage of P character, or the one having more percentage of S character? Surely it should be more percent of S character. That's what we are seeing over here, that this orbital is going to have the nearly 40% of the 40% exactly. They have said that 40% S character is being used in the terminal PO bonds. That seems to be the correct answer. And option number 4, option number D, was the stronger covalent character in the PO in the cyclic oxygen atoms. See, if you compare this stronger, it was not clear, stronger in comparison to what? If you are saying stronger in comparison to another PO bond or another PBr bond, that could be having confusing thing. So if you are comparing PO bonds, then definitely the terminal PO bond is going to be stronger. That is going to have a little bit more covalent character. And if you are having ionic character, we can see that there can be some like if the bond is a little bit breaking, that can be having less covalent character. If it is having, say, covalency increasing, it can be having a little bit more character. So more covalent character or stronger covalent character would be implying probably greater bond order. PO bond over there cannot be having greater bond order. We'll see in a moment there can be some reasoning of the electron delocalization from oxygen, the cyclic oxygen over here, onto something like that. That is one possibility which we can be seeing that is happening actually to certain much less extent. We'll see in our solutions. So what is our take from this discussion we have just had? First thing is that larger bonds are going to have higher percentage of P character. that's sure, longer bonds basically, and we have got shorter and stronger bonds, that is we should be having relatively more percentage of S character. That's what our reasoning would have been. And we go back to the Benz rule. It says that the atomic S character concentrates in the orbital which are directed towards more electropositive atom. So that we are basically saying, if you are having certain atom and if this is having going to have some positive character coming into it, then it can be attracting more of the electron density. That can be basically forming a relatively shorter bond, and the shorter bond can be having a relatively greater contribution coming from the more percentage of the S character. We'll see how that could possibly be happening. So this is the thing what we have been given, just to written them the same diagram. And there is something what we call isovalent hybridization, which is basically if you are using some say molecule, the same atom which is present, say a central atom, it may not be using the exact same percentage of hybridization along all bonds unless and until you are having equivalent bonds all around, like in carbon tetrachloride, like in methane, like in phosphorus, not phosphorus, like in any other symmetrical molecule, we can be having the same kind of bond schemes present. PCl5 will not be having the same thing because the equatorial versus axial bonds are going to have different percentage of P and S characters. That's what we have learned already. Okay, so what we can think is with respect to the phosphorus, when this is going to be the 4 bonds being formed, 4 sigma bonds, is going to be the case of sp3 hybridization basically, and sp3 hybridization, there is one d orbital remaining which is going to form the PO terminal pi bond. That terminal oxygen was basically forming one of the pi bond, that is coming as d pi, p pi bond coming from the phosphorus oxygen overlap. So this is the thing what is happening in the phosphates, and this was the one of the examples of, we can say, phosphate esters, bromoesters actually we should say more correctly, cyclic phosphate bromoester. That was the case what we have seen the given molecule. And here what we see, this can be the contribution when we are having this open like this resonance can be taking place very much easily like that. But if you talk about the resonance taking place from these bonds, the alkyl oxygen, this oxygen, if you think of, then this oxygen getting positive charge, this is having a relatively less contribution, or this oxygen. So basically alkyl oxygen, which is ester, like alkyl ester oxygen which is present, that will be having little bit much less electron delocalization because of the positive charge coming onto it. This is going to be having a relatively much less contribution in the resonance habit. That's going to be having basically less electron delocalization is possible in comparison to the negatively charged oxygen. So what we are saying, the non-bridging bonds with phosphorus oxygen, they'll be having significant double bond character, and those bridging bond means the bond which is connected to the alkyl chain further, that will be having relatively little double bond character. That's the difference we could have said. Out of these two things, we can say here there is going to be less covalent character, and in this case we can think there is going to be relatively more covalent character. That's how we have said the last option in this given options was not to be correct. Okay, so one takeaway we can take from here is that if this is oxygen over here, this electron delocalization can be taking place very much easily, and this electronic delocalization coming from the oxygen is going to be relatively much smaller. Now what happens if you replace this oxygen atom over here? If we replace this oxygen atom over here, sorry, if we replace this oxygen atom over here with some bromine atom, will that electronic delocalization be taking place in the same way? Probably not. This is going to be much smaller delocalization because of the much difference in the size of the bromine. This is one of the diagram, the three-dimensional basically structure for this molecule what we have been given, and in the cyclic structure what we are seeing, please note, please pay attention here, this lone pair in the cyclic position what we are having for this this lone pair what we have got, sorry my mistake, this lone pair what we have got over here, this is going to be anti to this phosphorus Br1. This is the phosphorus, these are the internal oxygens, and this is the terminal oxygen. So those lone pairs can be changing the situation over here with this bromine. Although we might not have explored that possibility, but that is what we have seen happening somewhere, what we call as anomeric effect. We'll see in a moment how that delocalization is going to take place, how that is modifying the bond length over here and the bond length over here, or the bond strength as such we can say. So this structure is going to be where this Br is going to be in axial position, and this PO terminal bond is going to be in the equatorial position in this 6-membered chair conformation of this given molecule. Okay, this structure you need to remember, because this electronic delocalization, what will be taking place over here, we will be seeing in a moment. These two bond strengths or bond orders or bond lengths are going to be modified as a result of what we know as hyperconjugation. That is actually a much less discovered thing, but this hyperconjugation over here, what will be taking place, this hyperconjugation will be changing the situation of this bond lengths and bond strengths. We'll see that in a moment. So this is actually the picture of that same molecule what we have seen here. The axial lone pair, we have two kind of lone pairs on this cyclic bridging oxygens. One is the one which is in the lone in the equatorial position, and one the back side is going to be on that. Basically this is the on the axial position, and this is the lone pair which was in equatorial position. That is not participating. The axial one is going to be participating into the hyperconjugation from lone pair into the sigma star orbital. If you have not learned that, we can skip this discussion of this 1 or 2 slides, but that is what is required to explain if you have learned in the biomolecules what we call as the anomeric effect. There, the equatorial methoxy group is supposed to be in the that glycoside methyl, when we are having alpha methyl glucopyranoside, there the axial conformer is more stable. That is what we have seen in the anomeric effect. Same thing is happening here. This lone pair from this orbital, which was the axial lone pair on this cyclic oxygen, is undergoing hyperconjugation into this orbital, this sigma star molecular orbital of this axial phosphorus bromine bond. How that anti-bonding molecular orbital and this bonds are overlapping, I'll be showing more clearly in the next slide. So the result of this electronic delocalization and hyperconjugation is that one of the bond is becoming stronger and one of the bond is becoming weaker. So with this anomeric effect, what we have seen, what is happening, this particular oxygen phosphorus bond is becoming longer. That bond order, this bond is becoming relatively, because of this thing, this bond order is going to increase, bond is going to be stronger, bond length is going to become shorter. And if you talk about this phosphorus bromine bond over here, then in the phosphorus bromine bond, this bond order is going to basically decrease. If the phosphorus bromine bond order is going to decrease, then this bond order is going to be decreasing because of the same result of hyperconjugation. That is what we can see. We have seen phosphorus bromine was going to have relatively less than 20% of the hybridization. Less than 20% of the S character in the hybridization, and cyclic oxygen to phosphorus was having 20%, little bit greater. You can say phosphorus bromine is going to be having a little bit less contribution coming from that. This is the hybridization scheme, how that lone pair present in the axial position is undergoing hyperconjugation into the sigma star. This orbital we can see is going to be the this orbital is going to be basically phosphorus bromine sigma star, and this is the non-bonding electron pair, that's lone pair in axial position. This is how anomeric effect was taking place, and the result of this electronic delocalization is going to be that we will be having some different percentage of the bond order is going to change slightly. This bond order is going to have the strengthened effect. This will be having weakened effect. So percentage of S character is going to be related with that changing in the bond strength. I think enough discussion about this question. That's all for now. Thank you for watching, and these have been all the questions in the section 1. I'll see if you guys like this. We can be going on to some of the next discussion about the subjective papers as well, if you feel, and if I see the comments, if you like the videos, if this enriches something in your knowledge, then please let me know in the comment section, and if that happens, we can possibly be going for the paper 2, that subjective paper, that also we can possibly discuss. Never mind. We will be seeing some next time. That's all for now. Thank you. Bye bye. Take care and keep learning.